Okay, I'm going to do a quick review of the free response question on your semester exam that you had to, the related rates question. And I'm going to do the one that was dealing with the conical reservoir. This is the question that mods 5, 6 you had, and if you are in mods 11, 12, you can flip the paper over and the one that I gave you back, your attempt, and I copied this question there for you. So this would be good review and good extra practice on your requiz. If you choose to do requiz, any of these could appear. So, and possibly different questions rather than A, B, and C with one question. I might just do 3 different questions. So here goes. I'm going to start by identifying information, and I did give you a point for just identifying that this first sentence is telling you a rate of change of volume. I focus on the units. It tells you right here cubic meters. So use that to help you. Cubic meters is a volume measurement. So I know that I have a dV/dt measurement. Rate of change of volume with respect to time is 25. Water is flowing from the reservoir, so we'll put negative in front of that. Cubic meters per minute. Diameter of the reservoir is 30 meters and height is 9 meters. So I'm going to need to draw a picture here, but I'm recognizing already that I'm going to have, as far as units, I'm going to have a volume unit because I'm filling this up or draining it. Sorry, I'm draining it. So I'm going to have a volume for my unit. I'm going to have a radius or diameter. I'm going to go with radius and a height. So far, I've got one match in terms of I've got volume and then rate of change of volume. So remember, I'm always looking for every variable that I end up using in my problem or in my equation that I make. I need to have a related rate to that variable. And if I don't, it could be something that I'm looking for. But if it's not something I'm looking for and it's not a given rate, then I'm in trouble. I've got too many variables. So I'm going to go ahead and list out the equation. Volume equation from geometry class for the volume of a cone is 1/3 pi times radius squared times height. So I'm looking at that equation, and I definitely have all the correct variables right here in terms of my equation. So I've got volume, I've got radius, and I've got height. I need to really look at what am I looking for in terms of rate of change. So if I take a look at that, part A, we'll just start with part A. Part A is asking for how fast is the radius of the water surface changing when the water is 6 meters deep. Radius of the water surface changing. And I know I'm ignoring the numbers right now because I really don't like to focus on numbers because a lot of them are specific to a particular point in time. So I'll get to that. So radius changing is going to be dr dt. So it looks like dr dt is my unknown rate that I'm seeking, at least in part A. So I've got dV dt. I'm looking for dr dt, which means that check radius is okay. So if I have my radius in my equation right here, when I take the derivative of this, I know I'm going to end up with a dr dt. That's okay because that's what I'm looking for, and that's a good thing. Same thing when I take my derivative here and I've got volume, I'm going to get dV dt on the left side, and I'm okay with that because there's my dV dt. So the problem I'm having right now is, the only problem I'm having is that my height right here does not have an associated rate with it. Read back through your given information. There's nothing about a rate of change of height, and there's nothing in your question about rate of change of height. It's not until you get to part B that they're asking you for how fast is the height changing of the water level. So I need to do one of two things. I can take my derivative and then try to plug stuff in, but I'm having you try to think about it ahead of time. Because what's going to happen is, first of all, you've got a complicated derivative. You're looking at product rule right here because you have two variables being multiplied together. So to correctly do that, you're going to have to use implicit differentiation embedded in your product rule. And the second issue is that when you get done with it, you are going to have a dr dt and a dH dt, which means you're going to have two unknowns, and you cannot solve for two unknowns at the same time. So I'm going to avoid that altogether. And I'm going to find right now, I'm going to find an expression that I can use that represents h, that I can replace h with, so that I can solve for it in terms of r or in terms of v, and then I can simplify my equation before I even go to take the derivative. So this is where our picture comes into play. So picture, I'm going to draw over here. Picture of what's happening. I've got a cone. And the cone is, I believe, 30 meters in diameter, but I'm just going to draw the radius and do everything in terms of the radius. So let's go from here. And my radius is 15. I'm putting that on there because the radius is not changing of the actual conical reservoir. Same thing with the height of 9 meters. So those are given at the top. Clearly my picture's not to scale, but that's okay. So the 9 and the 15 are constants throughout the whole problem. Now you do have a changing radius and height. And that's where this problem becomes a little complex, because there's actually a second triangle, if you will, or circle. There's a circle of water, whatever point the water is, and that creates a changing triangle as the cone gets drained that's going to have a specific radius and height at any given point in time. So what's happening is I have this small little red triangle, and then hopefully you can see my big triangle. I'll go ahead and highlight that one in green for you. That would be the 15 and the 9, and they end up being similar triangles. So the way that I'm going to relate these is I'm going to make a proportion, and I'm going to relate the big triangle, the radius, over the height of, 9, has to be equal to the ratio of the radius and the height at any point in time. So whatever my radius and my height is, it has to be equal to the ratio of 15 over 9. Now, there are other ways you could have done this. Just a quick recall from prior years of math. You could have related the two radii, 15 over r equals 9 over h, as long as you're matching them up in the correct order. So if you had a different thought, that's totally fine. I'm going to go ahead and cross multiply because, again, what do I want to do? I want to replace h right here, but I need an expression that says h equals something in terms of r. So I'm going to have 15h equals 9r, cross multiplying. And then I'm going to solve for h, and h is 9 over 15 times r. And I can do one step better because I can go ahead and reduce that, and that just gives me smaller numbers to work with. So that's going to be 3/5 times r, or 3r over 5, and that is going to become my h, 3/5 r. So h is actually completely gone. Let's take a look at what we're dealing with now. So going back to my equation, I now have volume equals 1/3 pi times radius squared times 3/5 r. Still not taking the derivative. I'm still going to keep simplifying. I've got 1/3 pi times radius squared times radius. So radius squared times radius is going to be radius cubed. And then I've actually got 3/5 times that, and I should have put that out front. The 3's will cancel. So I'm ending up with 1/5 pi. So volume equals 1/5 times pi times radius cubed. Take a good look at it. I know we just went through 4 steps there. To me, it's worth it to go through the time right now to make my derivative simpler. Last thing I'm going to check, as long as I can't simplify anymore, I know I'm good with my rates because I checked that. I eliminated my h from the problem, and now my rates match here. My rate matches my variable, so I'm good to go. There were no constants in this problem except for the 15/9, but there's no variables right now. In other words, my volume is changing and my radius is changing. So I can't plug in any numbers. I know it said something about a radius of 6. No, actually it gives you a height of 6, so we'll deal with that in a minute. Let's take the derivative. So I am 9.5 minutes into the problem. I'm finally taking the derivative. dv dt equals 1/5 times pi, because that's a constant multiple. So I'm going to write that. That just carries along. Now I'm going to do the derivative of r cubed, which is 3r squared, times dr dt, since I'm doing implicit differentiation. And from here, I really think you'd be fine to go ahead and finish it. I'll walk you through it, just so you can make sure you're good with this. Plugging in everything I know. So going up to the top, my dv dt was a negative 25. 1/5 pi times 3 times radius squared. Radius squared, I'm not sure what my radius is. dr dt is what I'm looking for. So I need to find my radius. That's interesting because I don't think they gave us a radius. So I'm going to go back, look at the problem. They said when the water is 6 meters deep, this is what I'm looking at right now. 6 meters deep is a height measurement, but that's okay. Don't panic. We need to find a radius. We have a really nice formula that's relating the radius and the height for us. Check it out. It's right here. So if my height is 6, then that's 3/5 times my radius, and I just need to solve for my radius. Or you could have gone back to this equation and just plug it in right there. I'm just going to go ahead and multiply by 5/3. So I have 6 times 5/3 is giving me my radius. Multiplying by 5/3 cancels that out, giving me just r on the right side. So 6 times 5 equals 30 divided by 3. My radius is 10. Just double check, make sure that makes sense. Radius is 10. Plug and chug. We just need to do some math here to solve for dr dt. So final answer is going to be dr dt equals, and I need to do some calculations. I would try to keep it in exact form. Let me know if you have troubles with that, but otherwise I'm going to let you go ahead and see if you can get to the answer of -5 over 12 pi meters per minute, negative because remember it's draining, so the rate of change of height, or sorry, rate of change of radius is going to be negative. It's getting smaller. That's approximately, if you're doing decimal version, negative 0.133 meters per minute. I would say you should be able to get the exact answer though as well. So that would be part A. Now before I close this video, let's just take a quick look at B and discuss what would we do for B, and then I'll do a separate video for C. How fast is the water level falling when the water is 6 meters deep? Pause it if you want to try this on your own. Otherwise, I'm going to give you a quick hint. I'm not going to do it for you. We're looking for what? Yeah, you're right. We're looking for dh dt this time. So notice how we started the other one. We tried to get rid of the variable h and get everything in terms of r. If you're seeing a pattern here, we're now we actually do know dr dt. So we have two options. We could keep this entire equation and deal with it. Do the derivative using the product rule. We could use our answer from the previous question, our dr dt, and then solve for dh dt. We don't have the two unknowns because we now know dr dt. Or the other option is repeat the same process, but instead of getting rid of h, get rid of r. In other words, take your work over here and solve for r in terms of h. You could substitute in right here and get an expression for r in terms of h. So what? R would be 5/3 h. And then keep your h over here, and then you'd end up with a dh dt. Okay, I'd encourage you to give that one a try and see if you can work that one out.